Okay, now this part is something that again begs your being human, your understanding of the fact of your understanding something um, which can't be put any simpler than it's stated. You just understand or you don't. When one straight line landing on another straight line makes the adjacent angles, right? What's an angle? Don't know. Equal. When they're equal, each of these angles is called a right angle. And each of these lines is said to be perpendicular to the other. Okay. Now, you might be saying, well, duh, obviously. But remember, angle has not been defined. Don't know what that means. Perpendicular is just being defined in terms of a thing that has no meaning. It could be, as I said before, purple elephants. But the only point here, I suppose, is the characteristic of two things being equal on either side of a line when it meets with something else. Whatever the thing is that is being said to be equal is not that important, as long as you have a feel for it. Quantitatively, one should comprehend that the idea of angle is not dependent on the length of things. This black curved thing here is meant to indicate the angle, right? The distance from here to here could be 1 centimeter, or it could be 1 light year, and the angle here would be the same. It's not. It is something that is independent of scale, if you like. One full revolution of a circle is said to contain 360 degrees worth of angle. How about that? An obtuse angle is an angle greater than a right angle, defined here. So in your mind, you can imagine like this picture. This one meets here, and there's more of this black curved part than a right angle. And if there's less, it's called acute. Boundary means the extremity of a thing, any kind of thing. If we have the notion of a thing, and if it has the quality of having size or measure, then its boundary is just works interchangeably with the word extremity. Boundary, extremity, same thing. A figure. Now, this is I don't know if that's common usage today. You'll usually see in textbooks refer to figure 6 or figure 7 or something, and that's usually not one thing. A figure might contain lots of information, text, and two things being compared, and who knows. But this is a specific, in this geometry, a figure is a specific word. It refers to Now it says a surface enclosed on all sides by a line or lines. Okay, so a figure is a two-dimensional thing, and it's enclosed, entirely enclosed by lines or one line. So it has a size, I guess. So a figure is a finite object in two dimensions, I think is another way of putting it. No, it didn't say plane figure, but I think it should have. Because you could imagine a three-dimensional figure, right? Like a box. Anyway. A circle is a plane figure bounded by one continued line, called its circumference or periphery, and having a certain point within it from which all straight lines drawn to its circumference are equal. You know that already from your millions of years of experience in high school. That there is a point, a circle has a center, and from the center to the periphery, the distance is equal no matter which direction you go. Unlike every other figure that exists, the circle has that property. Now prove that one. I mean, that there is no other shape that has that property in two dimensions. Okay. Referring to a circle, this point, the one with all the equal lines, is called the center of the circle. Notice the spelling. Okay. A diameter of the circle is a straight line through the center terminated in the circumference. I guess that they mean you draw a line right through the circle, through its center, and cut it off at the extremities or the periphery of the circle, and you have a diameter for the circle. And I don't believe it would be very difficult to show that the length of any diameter, is the same, no matter what way you look at it. It's symmetric. It doesn't matter which way you go. You're going to get the same length. Not a semicircle. A semicircle is a figure contained by the. Okay, so we cut through the diameter, contained by the diameter, and the part of the circle cut off by the diameter. Now, again, this is a bit ambiguous. What do you mean, the part of the circle cut off? Couldn't it be the top that was cut off? Or the bottom? Or both? And I would agree with you if you felt that way. Probably a better wording for this would be to make it unambiguous and say, and the upper part or something cut off. Of course, we haven't a definition for up. Now this one is not ambiguous because there's a big part and a little part. And this is called not a segment, but a segment. Contained by a straight line and the part of the circle, and the part of the circumference which it cuts off. Well, now that is ambiguous. This, I guess, also is a segment, right? You can have both, a little segment or a big segment. According to this definition, either side counts as a segment, though the image seems to indicate the smaller part. A figure contained by straight lines only is called a rectilinear figure. You now know something that about 99.9% of the planet doesn't know. This word rectilinear. Something that everyone learned in high school and everyone forgot about 2 minutes after they learned it. A triangle is a rectilinear figure with 3 sides. A quadrilateral, 4 sides. A quadrilateral has, as you can see, is characterized by 4 points that define 4 sides. And so it's a specific kind of shape. You could make a, for instance, with 4 sides. You could do a kind of zigzag or something, I think, and get a 1, 2, 3, 4. You could do weird things with the 4 lines and not end up with a figure like this. So this is saying that it's the kind of thing that resembles a box, right? Because it has diagonals and 4 sides, and it's enclosed. It's bounded. It's a figure, right? So there you go. There are some things you can draw that aren't figures at all, with lines, just by drawing straight lines, and that won't, define a single region. It won't be enclosed. You can draw one of those star things. Sometimes they're closed, and sometimes they're kind of half open and half closed. Anyway, a polygon is also a figure with more than 4 sides. I wish that was true. That would be true, perhaps in Euclid's day, but the polygons that people seem to find most interesting are the ones that are complicated, and the lines cross each other, and you get like strange holes and things in them. I can draw one with this, and it'll complain. But when you do it with lines, it won't complain. Let's see now. If I draw a line and then I keep connecting them, I could do this. This is a polygon, apparently. Alright, now tell me what's inside and what's outside. Looking at this figure, like for instance, are the points in here, are they inside the polygon, or are they outside of it? Or the points here, are they inside or outside? If these ones are outside, if these are inside, then that would make these ones outside. It seems kind of strange, doesn't it? And so these are the ones that people love to work with because they're very interesting, and there's an interesting mathematics that goes along with studying these polygons and trying to figure out various principles about them. And it turns out that there are applications for that kind of stuff. We don't have to worry about that. We don't have to worry about that, sorry. Okay, now these ones, I always get these two confused. Almost done, well, almost done. I'm just going to finish the definitions and I won't go on any further. When all the sides are equal, it's called an equilateral or equilateral. Equilateral. Equi for equal, right? However, if two sides are the same, then it's called an isosceles. Iso means equal, and scale, same scale, sort of. It's the way I would read that. Is in its scaling, same, but it's not. Only two sides are the same, and the other side is not the same. Well, it could be the same. Whether or not this is a strict definition is not certain. If it has two sides equal, it's an isosceles, true. But that doesn't imply that the third side is not equal to the other two, as far as this definition goes. Oh no, it is. Okay, it says only two sides. Okay. So it's not ambiguous. This one is definitely 100% certainly not equal to these two. And either of those two. In length, that's important. When Euclid speaks of equality of things, he's speaking of equality in measure, and different forms have different types of measure. A surface has area, a line has length, right? Angle is angle. If two things are the same, or two things have the same measure, and that measure happens to be length, then we're talking about the sides. If it's area, then we're talking about the an enclosed section or something. Scaling. For some reason, I don't know how they came up with this word. It's a triangle with no two sides being equal, and they don't even give a sample. Well, here's one. Okay, that's a scaling. These are all different. A right-angled triangle is one that contains a right angle. I don't know if you recall, but it turns out that one can prove that the angles of a triangle, the interior angles, if you add them all up, no matter how you draw a triangle, it always comes up to the same number. If you're speaking of degrees, then it comes out to 180 degrees, a semicircle worth of angle. Two right angles. Well, if a triangle contains two right angles and it has three angles and one of them is a right angle, then it follows that the sum of not only is the sum of the other two another right angle, but they must be, the other ones must be smaller than this one by definition. An obtuse angle is one that has an obtuse angle. Notice the right angle does not contain an obtuse angle. It almost does. It's right on the border. Now, it's possible for a triangle to contain an obtuse angle, and it's also possible that a triangle not contain any obtuse angle or even a right angle, such as this example. Because there are three things, you can make three things, all of which being less than a right angle, which is two of which makes a line, right? So you can make a three-dimensional figure with all angles being less than a right angle and have it still add up to a full half turn or a half turn of a circle. Okay, a square, all the sides are equal and all angles are right angles. A lot of people mess that one up. If you want to, if you're a teacher and you want to mess up your students, you know, especially if you're a university professor and you really want to embarrass them, is you know, ask people to ask your students to define a square, right? Most of them are going to forget to add the second bit, that all of these angles have to be right angles. It is, people generally take it as given that if all the sides are equal, that it must be a square. Well, that's not true. If you've ever tried to build a house of cards, then you know that that's not true. A square is not a four-sided, equal length-sided figure is not rigid. Like a triangle is rigid. It won't move. You can't deform it. But this here you can deform as shown here. All of these sides are the same length, but the angles are not right angles. And that's called a rhombus. Okay, rhombus. And again, if you can hold that word in your mind, you now know something that most every person on the planet doesn't. Though they heard it in school, they heard it once and forgot it immediately. Oblong essentially is a rectangle. It's right angles and the opposite lengths are equal and not the same. So that's what we normally call a rectangle. A rhomboid, otherwise known as a parallelogram, is that which has opposite sides equal to one another, but all of its sides are not equal. No angles right. Hang on a second. This is a parallelogram. No, sides equal. Sorry. Has opposite sides equal. Okay, that's fine. And then no right angles. So it's a rhomboid. Sorry, an oblong that's been pushed to one side. It's a bent oblong, just as a rhombus is a bent square. It doesn't say parallelogram, but today's term, in today's lingo, that's a parallelogram. Now, at this point, the real genius of Euclid is demonstrated. At this point, we just simply call everything else this, right? I'm sure that you could think up names for all sorts of different kinds of figures, but instead of doing that, he just stops here and says, "Look, that's enough. Okay, everything else is called a trapezium," and that's the end of it. Parallel, straight lines that have the characteristic that this is an old word, being produced in both directions. To produce means to extend. Because actually, it must have been mentioned earlier on. It's given the word to produce is given meaning somewhere up here. Where is it? I don't know why it's not more emphasized, to put in bold or something. Defining point. Well, somewhere in here it says, it tells you what produced means. Maybe it's afterwards. I have it written down actually. Oops. Actually, I do want this. I don't remember which one oh, this one maybe? I put it in a special color. Here, this definition. It's in there, it's right near where I was looking, I don't see it. A line is said to be produced when it is extended, prolonged, or has its length increased, and the increase of length it receives is called the produced part, or its production. Okay, fair enough. That's what that word means. So it's like the extension. We would say extension. Now, did I cover everything? I'm not going to go through the operators. And that's it. Next is postulates and axioms, and a few more definitions, which I don't think it's of any use to go through them. It's better to wait for them to come up. As they come up, you can refer back to this page to see what they mean. These might be familiar to you, therefore, because these have to do with ratios. A is to B as such and so is this and that. QED, that's the thing you write down when you've completed demonstrating what you intended to demonstrate. And problems, theorems, postulate, axiom, and so on have these loose meanings. In fact, these types of words have never had a definite, strict meaning. Why isn't when you solve a problem, why not call that a theorem, right? And that's just that's something that people know. If you show that balls rolling down when the incline is 37 degrees down an inclined plane with no friction, the acceleration is such and so, right? You could call that a theorem, but really that's a problem. It's a very minor particular case of a much more general principle. Okay, that's it for this one. I hope those definitions made sense. Sure, this is just labeling. There's no. This does not teach one anything except words. This one again really is not that helpful. It's sort of telling you what you already know, and maybe even causing some confusion, but it all has to be said so that when it comes up and you're reading a sentence and you're not sure what's being referred to, then you check back these definitions and you'll find that everything has a definition that I've seen anyway so far in this book. Okay, that's it. See you.